Morning, student. Today we are going to understand the internal resistance of a potentiometer, internal resistance of a cell using the potentiometer. So this is the circuit of potentiometer. Here, these are the wires. This is the wire of potentiometer, and it is stressed over the thick copper strips. These copper strips must be thick, otherwise their resistance should be kept small. Their resistance should not add with the wire resistance because these are series with the wire. Okay, now here it is a this is the cell, and this is the internal resistance, and this is a key, and it is connected with the wire, and it is this cell is used to send the current in these wire. Okay, and this is a variable resistor which adjusts the current in the cell. And we once we arrange the experiment, we will not change the value of this R and kept the current is measured by this ammeter. Current should be kept constant, current should not change while taking the reading from the potentiometer. Right, now this circuit is called as primary circuit, and now this is the cell of EMFE and internal resistance R. It is here it is the cell whose internal resistance is to find, and here its positive terminal connected with A, and its terminal are short circuited by this resistance box R, and we will use any resistance from this resistance box R, and this is a key connected with it A. Okay, so this is the cell whose internal resistance is to find, and now it is connected with this galvanometer, and now this wire at this point, here it is the jockey is a device which give the soft contact to the wire of the galvanometer, wire of the potentiometer. Right, so this is about the potentiometer circuit. How we find the internal resistance of the cell, of this cell. First we let this key open and we find the balancing length. Okay, we find the balancing length means then we go for the balancing length, slide the jockey over the wire. Okay, and second we keep the we close this key and put a resistance box, and then we balance the terminal potential of the cell, and we slide this wire, we slide the jockey over the wire and find the balancing length. These are the two steps. So this is the first, this circuit can be drawn like this. Here in place of these wires, we just take one wire from A to B direct. Okay, but this circuit is only for to explain theory, but in actual practice potentiometer will be drawn like this also in exam. Okay, so here everything is same. Here this here everything is same, variable resistor, battery, and this A point and this point. Right, and this is the this circuit is called as primary circuit, and this is called as secondary circuit. So here the secondary circuit as it is, as we have here, and this is the primary circuit. Now first of all we take the first step here. What we do, we let this key open, right, this key let open. So if this key is open, then no current will pass through this way, and then we can remove this. If no current pass through, then there is no use of this resistance. So now we will only this circuit. If key is open, now we slide it over, this jockey will slide over the wire of potentiometer. Here it is not connected, now is not connected with the wire. Now as it is not connected with the wire, no current will pass through the galvanometer because it is not a closed path. So terminal of the cell will be equal to EMF. If I is equal to 0, this is the formula of the terminal voltage of the cell. V is equal to E minus IR. If I is 0, so V CD. CD is the terminal of C and D. These are the terminal of the cell. So if I is equal to 0, so VCD is equal to E. And suppose the EMF of the cell is 20 volt, this cell, suppose. So this is the potential, the terminal voltage of this cell, CD is 20 volt. Or here I split this 20 volt, plus 10 and minus 10. The difference of plus 10 and minus 10 will be 20. Now we slide this wire over this, we slide this jockey over the wire, and suppose at J1 point it gives null point. So when we give null point, the potential across this wire must be also equal to the terminal voltage of the cell. It is 20 volt. If the voltage of the wire, voltage across the wire which is balancing the terminal voltage of the cell is 20 volt, then it will give the balance points. The galvanometer will not give the any deflection. So voltage across the potential difference across the cell is 20 volt, and the potential difference across this wire must also be 20 volt. Then there will be no current through the galvanometer. How we can say here, this 20 volt can be split plus 10 and minus 10, then difference will be 20. So here it is plus 10, it is plus 10, so there is no potential difference, current will not come here. here it is minus 10, here it is minus 10. No potential difference, current will not go here. So current will not come in this path. So there will be no current through this galvanometer, and this is the null point. Why galvanometer does not give any deflection? The potential difference 20 volt means plus 10 and minus 10 is equal to the potential difference across the potentiometer wire. It is the plus 10 and minus 10. So it is again the 20 volt. The difference of the potential will be 0. No current will pass through the cell as well as galvanometer. So now you come, we write the first step, step number 1 or case number 1. When key K is open, the suppose potential drop across the L1 length of the potentiometer wire balances the terminal potential of the cell at null point. Here it is written that suppose when key is open, this key is open, so what happens? The potential difference across L1 length, AJ1 is L1, from here to L1, the potential drop across this length balances the terminal potential of the cell, or which is equal to the EMF, because no current pass through the cell. Here this is the terminal potential difference across the terminal of the cell. VCD is equal to E minus IR. I is 0 at null point, there is no current passing through here, we have seen. So I is 0, so VCD is equal to E. Okay, and now what will be the potential across the wire? Potential difference across the wire, the formula we have derived already. V is equal to KL. So balancing length is L1, so potential drop will be V is equal to KL1. Or here this point is A, this is J1, so AJ1, VAJ1 is equal to KL1. Or at null point, this voltage across AJ1 or voltage across CDR equal. So VCD is equal to VJ1. What is VCD? E. This is equal to E, terminal voltage of cell, terminal potential of cell. And this or what is KL? This is the potential drop across the wire. Okay, so E is equal to KL1. This is the first step. Now in the second step, we keep this key close. हम इसको बंद कर देते हैं. Now if we close this key, what happen? Even if it is not connected from here, this resistance applied from resistance box will draw current from the cell. Now this is the closed path, and it will withdraw the current from the cell. Now even if it is the if it is not the null point, current keep on flowing through the cell. Current keeps on flowing the cell, and current is not zero. Current will not zero through the cell, and if this I is not zero, VCD will be less than EMF. So before in the first case voltage was 20 volt, now the voltage will be less than 20 volt because I is not zero. If I is not zero, so E will be get subtracted from IR, and VCD will be less than E. So now in this case, and this voltage is called as terminal voltage. So second case is this one. This is the second case. Here we have put this external resistance. External resistance changes the terminal potential of the cell. So it could be 18, 19 depending upon this resistance, right? Here I explain with an example. Let us see it. Here suppose this resistance is 8 ohm. So current through this closed path will be E upon R plus R. What is E? E is 20 volt. EMF of cell is 20. I am doing the calculation of this secondary circuit. R is 2. This is the internal resistance of the cell. This is 2 ohm, and external resistance is 8 ohm. So it is 2 ampere. Now what is the terminal voltage of the cell? IR. This is 20 and I is 2, or R is 2 ohm. So this is 2 to the 4. This is a 16 volt. We can also find out another way, I into R. I is 2, or what is the external resistance? This external resistance is 8. External resistance is 8. So it is again 16 volt. So terminal voltage is 16 volt. Now in the second case, suppose now I change this external resistance 8, in place of 8 I taken 18 external resistance. So what will be the EMF? This is a 2 plus this external resistance is 8. So 20 by 20. Now it is 1 ampere. Now what will be the terminal voltage? V is equal to E minus IR. What is E is 20 minus what is I is 1, this is 2. This is 18 volt. Now this E is 20 cell is same. I is 1 ampere, and internal resistance is again 2 because cell is same. So E 20 minus 2, 18 volt. Or we have another formula, V is equal to IR. I is 1 or R is 18. So 18 volt. So terminal voltage can be calculated from two ways, whether you calculate IR or E minus IR. Okay. So if you change the external voltage, if you change the resistance, then terminal voltage will change. Before, when external resistance was 8, terminal voltage was 16. When external resistance has become 18, now terminal voltage has become 18 volt. Similarly, so when you change the R, the terminal voltage CD, I have given it name CD, will change. Okay, it keeps on changing. This terminal voltage keeps on changing if you change the R, and if this terminal voltage changing, the balancing length will also change. right? Greater the potential, greater will be the balancing length. So here I have taken the case, if I am taking, it is of 18 ohm. So 18 ohm case is this one. So if it is 18, so in this closed path, 2 plus 18, 20, 20 plus 20 upon 21 ampere. So terminal voltage is 18. If this voltage is 18, so we will balance the 18 volt. Now I have break this 18 volt plus 9 and minus 9. And voltage, suppose at null point this voltage will also be 18. Null point suppose obtained at J2. So it will be again 18. I split this 18 plus 9 and minus 9. Now what happened? This is plus 9, this is minus 9. So current will not come down. Here it is minus 9 and it is minus 9. So this point will be also, 9 volt. This is 9, so this will be also 9. So what happened? If it is 9, it is minus 9, it is minus 9. So current will not come down. So if the current will not flow, galvanometer will not give any deflection. So what is happening? Current is not coming here, current is not going, but current is keep on flowing here. The current keeps on flowing. Similarly, current of this cell keep on flowing from this to this here in this way, and no current will flow through here. So when the galvanometer is not giving any deflection, voltage across CD is equal to voltage across this wire from A to J2. So here now I write it further to complete it. Suppose now here you see, when key K is closed, then suppose potential drop across L2 length of potentiometer wire balances the terminal potential of cell. So in this case, when key is closed, we have closed the key. Suppose potential drop across L2 length of potentiometer. This is the L2 length, balances the terminal potential of the cell. So here in this case, terminal potential difference of cell, terminal potential difference VCD is equal to E minus IR. Here I is not zero. You have seen I is not zero because this cell, the terminals of cell are short circuited by this resistance. This is withdrawing current. So I will not be zero. Even it is null point. You have seen, even if it is null point, current will not flow here to here or here to here. Here it keeps on flowing here. So I is not zero. So VCD will be less than EMF. And suppose VCD is equal to E. Yes, suppose we have VCD is equal to V. This is the terminal. Suppose this is we have suppose it, right? Achha, now potential. Here I have written potential difference, yeah, drop, whatever you say, potential difference and drop. Potential drop across L2 length of potentiometer wire. This is VAJ2 is equal to KL2. This is equation number. Now this is equation number 4, and this is equation number 5. At null point, these two are equal. At null point, what happened? VCD is equal to VAJ2. So what is VCD? VCD is equal to V, or this is KL2. Now we have the relation. Now we know that we directly write. We know that हमारे पास एक relation है. We have a relation R is equal to R L1 over L2 minus 1. So what is R is equal to, we have a one relation which relate E1 over V1. This relation we can derive this relation R equal to R. This R is the resistance, this resistance, this R is this resistance, and V is the terminal voltage. This R corresponding to this V. Greater the R, greater will be the V. EMF is constant, or R is the internal resistance of this cell. It is self internal resistance. And this terminal voltage, so when the value of R change, V change. Now what is the E and V? From equation 1 or 2, we put R equal to KL1 or KL2 minus 1. K cancel. So R is equal to L1 upon L2 minus 1. So what happened? L2 keeps on changing when you change the R. So how we find the internal resistance? First you keep this key open and you find the balancing length, that is equal to you find the balancing length, that is equal to K into L, you balancing length L1, and then in this case it balances the terminal potential of the cell, which is equal to EMF, because no current pass through the cell. So E is equal to KL1. And in second case, we short circuited by this key is closed, then terminal are short circuited by this resistance, and current keeps on flowing through the cell, so I is not 0. So if I is not 0, the VCD is equal to VCD less than EMF. Suppose this is equal to V, and in this case the potential across the wire KL2. So null point these two will be equal. VCD is equal to AJ2, V is equal to KL2. So one, in first case when key is open we balance the EMF, and in second case we balance the terminal potential difference. Now we have the relation internal resistance of this cell, and this is the external resistance, and this is the EMF, this is the terminal voltage corresponding to this R. We put the value. So this is all about L1. L1 is the balancing depth of EMF, L2 is the balancing depth of terminal potential difference corresponding to this resistance R. So this is all about the internal resistance of the cell. So thank you. Next